Hello and welcome. Today we're going to talk about regions in the complex plane. So this might seem somewhat mundane, but what we're really going to be doing is a lot of what I'd call set theory and a lot of definitions or terminology. Okay, so this terminology we're going to develop here today. We're going to keep using for the entire course. So it's a good way to just sort of we can all speak the same language and all be able to refer to the same thing. So some major ideas, though, what we really want to establish is the idea of nearness. Nearness. Okay, so let's now think about the real line. Okay, so if I'm on the real line, like that, and I have some point x, x naught, let's say, and I want to know, so I want to find, a set of points near x naught. So I might say a set, an epsilon value. Say I'll say epsilon of 0.1, and I'm going to say that all points near x naught are distance, 0.1 from x naught. Okay, again, this is a fairly simple idea, and I could set epsilon to anything I like, but let's say I defined 0.1 to be what I'll call near x naught. So I want to say maybe a neighborhood. I'll call it n of x naught, comma epsilon, and that's going to be the set of all points x given, and that's usually when we put that little vertical slash, it means given, or subject. Sorry. Sorry. Subject. Oh, subject to constraints. Subject to the constraint that any x that is minus x naught is less than epsilon. Okay. So in this case, we can say, well, that's right there and there. I'm going to say that this distance right there is 0.1, and that distance there is 0.1. And then this whole set there, that's what I'm going to call neighborhood x naught, comma, 0.1. And now this is a set. Okay, so there we go. There's our set. And we're going to call this a neighborhood. Okay, so now what we're going to do here is define the same idea of a neighborhood in the complex plane. So this set is our neighborhood. So let's go to a new thing here. Now, so neighborhoods in the complex plane are now, we're going to write them like this, and z naught, comma epsilon is going to be equal to the set of all z points such that the modulus of z minus z naught is less than epsilon. Okay, let's write what that would look like then in the complex plane. That, like that. So we have a point, maybe z naught is right there. And the distance means that any point, so if I go out there, maybe some epsilon value, and I can draw a circle around that, like so. So I got to get my circle looking good there. Okay, so the neighborhood then is every point within that disk, all right? And that's what this expression means. All right, and so that's a neighborhood, and that's now, we can say any neighborhood of a point, and that's what we mean. We mean this set of all the z value, of all the complex numbers that are some epsilon distance from z naught. And so another definition we want to have is that of the deleted neighborhood. Okay, and a deleted neighborhood we'll write as dn z naught comma epsilon, and it is simply the points z given that z is within the distance epsilon of z naught, comma, but z is not equal to z naught. So then this is essentially then just excising that single point from our set. Okay. So that's a pretty straightforward definition, and that happens to be important sometimes when we're talking about regions of the complex plane. So now we want to talk about some very important ideas here. When we're talking about a set, so if I say S is a set a set in the complex plane, okay? So I could write this as S is a subset of our complex numbers. This subset of the complex numbers, we want to define certain properties of sets in the complex plane. And this could be, the same is true for lots of different sets, not involving complex numbers, but other things. But the idea of an interior point. So an interior point, Z, that's inside, that means it's an element of S. I'm going to put little capital on that to just help signify this set. So Z is an element of S, and that epsilon means element of. Okay. An interior point, Z, is a subset of an element of S that there exists. I'm going to put that means there exists some neighborhood of the point. I'm going to call this Z naught epsilon that is wholly inside S. All right, and what we're talking about, if here's our set in the complex plane, that's S. And I have this point Z naught here. It's an interior point only if I can find a neighborhood, i.e. I can find some epsilon value that's around that Z naught that's completely inside of S. Okay, so that looks nice. So of course, other points like this. So if this point is on the edge there, if that's our Z naught, this is not an interior point. Because no matter what neighborhood I draw around it, there's always some points of that neighborhood. I can draw this really small, I can draw it really big. Any neighborhood I draw, any neighborhood that I take around that point Z naught, always will include points that are not in S. Okay? And therefore, it is not an interior point. And so that makes sense. This is a really formal idea that we're establishing, but it's a very intuitive idea that sets like this have some interior points. So here would be another interior point. Points that are really, really, really close to the edge, I can draw a little tiny neighborhood around it for some value of epsilon that's wholly inside of S. Okay, so that's the idea of what an interior point is. Okay, so let's now go to a new layer. And now let's, a new page, say here. And so now let's talk about other properties of sets. And I'll keep using S as my example set, and we'll keep adding some other properties we can say. So now we want to have some descriptive terminology to describe aspects of sets. So the first idea is that of being an open set. An open set is a set in C in the complex plane such that, I usually put ST for such that, every point in S is an interior point. Okay, so what do we mean by this? Let's see if I. So one example here is that of the neighborhood. So a neighborhood z naught comma epsilon is open. Okay. So why is that true? Well, we know that the neighborhood is equal to z, where z is less than or uh, everything that's less than epsilon distance. We notice that it's strictly less than, right? So that means that when I draw this set, like that, so if I draw a neighborhood here, all right, so has some center to it right there. All right, every point inside of it, I can draw yet another little neighborhood around it. But the idea here is that with this neighborhood is those points on the boundary are not included in the set itself. Okay, and that's because it's strictly less than. So every point, any point in the set, they're all interior points. And if I have a point on the edge, that's not actually included in my neighborhood. So that's an example of an open set. Of course, a closed set. A closed set, then we need to establish some other terminology there. We have to understand this notion of boundary. So a closed set is, well, it's not open, for one thing. A closed set is not open, but it's actually more than that. A closed set is a whole different type of thing. So we have to establish one more definition, that of a boundary point. A boundary point is simply a point. Is a point where every neighborhood. Sorry, a boundary point has to be always in relation. A boundary point is always of a set S. Okay, so a boundary point is a property of it's an element of a set that has a certain property, and that's always in relation to the specific set we're referring to, and that is that so if Z naught is a boundary point if every neighborhood, and that means any epsilon value, is not a subset of S. i.e., that is, I can write neighborhood Z naught comma epsilon is not a subset of S. And that's certainly clear. If I take a boundary point there, and if I draw a little neighborhood around this set, it's always going to contain some points that are outside of the set itself. And that means it's a boundary point. Okay. And so now we can define a closed set is S is closed when it contains all of its boundary points. Okay, so in this case, I can always close my neighborhood, right? So that in case, if I want to take this set now S, which is this neighborhood here, and if I wanted to include all these points into the set, then it would be closed. Okay. All right. So that's a very neat thing. So we can actually write that as follows. So the closure of S is basically S union all all boundary points. Okay, and so in this case, now if I wanted to close, so here's my example, a closure of the neighborhood would then be, I can call that this, I can call it CN maybe for closure of the neighborhood, and that will simply be the points Z that are epsilon distance or equal to epsilon. And that's the big difference here, is now we include a less than or equal to sign for that distance. So we have our neighborhood, which also includes all those boundary points all around there that are included, as well as the interior neighborhood. Okay, so that makes sense then. All right, so again, these ideas are pretty straightforward. So now we have another idea. So now let's come up with another property of sets, and that is the idea of a connected set. Okay, so we say that S is connected if for every pair of points, I'm going to call it Z1 and then Z2, that are elements of S, there are finitely many line segments all inside S that join end to end the points Z1 and Z2. So the idea here is that, let's say I draw a set in the complex plane. It goes like this. And I take any 2 points. So in this case, I'll take Z1 to be that point, and I'll say Z2 is this point right here. Okay. And then I should be able to, so it should be that I'll be able to, these 2 points, this set here is obviously connected just by looking at how I've drawn it. And I can take a line segment there and join another line segment, and I can take finitely many line segments. And it doesn't really say how I do it. I can zigzag these line segments, whatever it is, but they have to all be contained inside of S, and then they join. Okay, so that has to be true for every pair of points. So maybe another example here of a non-connected set would be a set like this. And then I have another set like another piece of the set that's like that. All right, and clearly there's a gulf between those 2 sets. So here's a point there, and there's a point there, and there's no line segment that's contained completely within S that will join those 2 points. Now, certainly it's true if I take another pair of points, I can find a finite set of line segments that does connect them, that's contained in wholly, but it has to be true for every set of points. And so that's the other item. So that's another adjective we use to describe sets. So a closure or a closed set, that's we say a set is closed. That is an adjective to describe something about the set. Or a connected set. So we've been talking, or an open set. Those are all ideas or are all modifying or sort of aspects of sets. All right, so let's talk about another example real quick here. So let's talk about the set. It's going to be the set neighborhood of 1 plus I, comma 1, union neighborhood 1 minus I, comma 1. Okay, so let's look at what this set looks like. Going to have to draw precisely. Okay. And then now I'm going to, let's try doing this then. So here we go. So we'll have a point here. That's our I. Oops. Here's our I axis right there. Okay. And then there's a 1 right there. Okay, so now together we'll put these two sets up there. So there's the point right there. And then there's also minus I down here. And there's another point. And now we're going to draw circles around this. That goes like that. And there's another line there. Oh, that doesn't seem to... I didn't scale these very correctly, but hopefully we can move those in. Anyway, sorry about this. I'm still learning how to use this new tablet that I have. So let's try redoing that. It goes something like that. Okay, so so this set contains two pieces, but and I didn't really draw it precisely. It should really just come up right to there. Remember, both of these sets are open. So the union of open sets is also open and contains no boundary points, right? So that means the point z equals 1 that lies right on that axis, z equals 1, is not an element of S, right? So if I have 2 points, say a point here and a point there, also this set is not connected. Okay, and it's also not closed. Okay, so that's the idea, and that's just another example we can have to understand how this thing works. So we see now if I were to take the closure, if I was to take S is now equal to, I'm going to call this CS for the closure of S, and I say that Cn 1 plus I comma 1 union Cn 1 minus I comma 1. Then this is a closed, obviously, and also connected. In this particular example, the closure of this set makes it connected. That's not always true, that if you close a set it makes it connected, but in this case it actually now z equals 1 is included in CS, this new set. And then any 2 points here, if I have a point here and here, I can always find a line segment. As long as it passes right through the point z equals 1, I can get from there to there. I can always find a way to connect 2 points to each other. So there's another example of how this works. All right, so now let's go to a new example. And so finally, we have another idea, and this idea gets a little bit more subtle. We're going to talk about an accumulation point. So we say that z naught is an accumulation point if, it's an accumulation point of a set if H deleted neighborhood of z naught comma epsilon, that is, and that means for every epsilon contains at least 1 point of S. All right, so let's talk about an example of an accumulation point. So the idea of a so let's talk about our neighborhood again. So we'll talk about a neighborhood of some point. We'll call it W comma epsilon, and we can draw that as such. There's our complex plane. And then we draw a neighborhood there. Okay, so an accumulation point means that if I take a point there, now obviously if I put a little epsilon ball around it, and I say, if I put this little deleted neighborhood that doesn't include the one point that it's centered on, clearly it intersects with some other point of the set, right? So that's and now if I take a boundary point, of course I can draw a little deleted neighborhood around it, and it certainly intersects right there with some point of the set. So that, of course, is also okay. So in this case, the boundary point is an accumulation point. So now what about other sets? So let's try, so that's one example of this neighborhood of some point W. That certainly is an accumulation point. So now let's talk about another example. Let's talk about this set S, and now we're going to talk about a set that's clearly, it's a little different than we've talked about before. It's going to be a set of complex numbers I over n for n equals 1, 2, 3, 4, 5, 6, and so on to infinity. Okay, so what does this set look like? Well, I'm going to draw another axis. All right, so let's draw out what these points are. So one thing we'll do is up here at I, so for n equals 1, we have the point that's sitting there right at I, and then we also have the point for n equals 2, we have the point I over 2, and then we also have I over 3, that point, and then I over 4, that's right there, that point, and then I over 5. And you see that they start getting closer and closer together as they get closer and closer to z equals 0 right there. So is z equals 0 an element of S? And the answer is no. No value of n will create z equals 0, but z equals 0 seems to be close to our set S, right? If this is our set we define. So the point z equals 0 seems to be close. So in fact, z equals 0 is an accumulation point. And that's because if I take any deleted neighborhood, if I take a little neighborhood around that, it will always contain some elements of this set. There's always something. For instance, if I pick, so if I take any deleted neighborhood here, it will always contain some points. Now let's try another point. Maybe is z equal to I over 2 an accumulation? An accumulation point? And the answer is no. I can draw a deleted neighborhood around this set that's small enough. Say if I take epsilon is equal to 1/10, right? If I take epsilon equal to 1/10, that'll make a deleted neighborhood that's small enough that it encloses only I over 2 and will not contain any of the points next to it. So it will not contain I over 3 and it will not contain I or any other point of S. So I over 2 is a member of the set, but it is not an accumulation point. So again, I think a lot of times we think of we have this conception of sets as always being these sort of blobs of points. But of course, these sets right here, this is a discrete set. And so it will always it doesn't look like a blob of things, but rather just a collection of points within the plane. So let's talk about some other some other aspects of this set. So what other things about this set here? I'm going to put it down there. One thing, it's closed. And I'd say that it's closed because it contains all of its boundary points. But another thing, well, it doesn't contain all of its boundary points, but it's certainly closed. And another aspect of it is every point is a boundary point. Okay, but there is this point z equals 0 that we're heading towards, and we could call that a boundary point as well. So that's an example of another interesting set we could study. So now we have some basic definitions that we're gonna use well throughout the rest of this course for sets in the complex plane. So that summarizes everything we have to say about all these things. So thank you very much.